Problem 59 from Chapter 20. We're asked to find the wavelengths in free space for parts A and B, where we have frequencies of 5 times 10 to the 19 hertz, and we also have 4 times 10 to the 9 hertz. So for part A, well, for both of them, we're actually going to use this formula, right? Wavelength times the frequency is equal to the speed of light. So we solve for the wavelength. And then for part A, enter in the speed of light, 3 times 10 to the 8, we'll just write it out more explicitly, meters per second, over 5 times 10 to the 19, 1 over seconds, right? That's hertz. And that'll give you a value of 6 times 10 to the negative 12 meters, because this will cancel with this. And that gives you a value of exactly 6 picometers. So there's the first answer. The second answer, 3 times 10 to the 8 meters per second, over 4 times 10 to the 9, 1 over seconds. That cancels, and then we get 75 millimeters. Pretty straightforward problem. We're just plugging into this formula here and solving for lambda. Next problem, number 60. We're given a scenario with a diathermy machine in physiotherapy. I don't know if I'm saying that right. I've never seen this before. But it apparently gives you EM radiation until you feel deep heat in your tissue. Okay, we are told at what frequency we're broadcasting the EM radiation. 27.33 megahertz, which is 27.33 times 10 to the 6 hertz. So again, it asks for what is the wavelength. We use our formula. C is equal to lambda times F. Lambda is equal to C over F, which in this case is 3 times 10 to the 8 meters per second over 27.33 times 10 to the 6 hertz, which is 1 over seconds, right? So that cancels, and then we're left with, I'm going to move over here because I've run out of room. It's having a hard time with this eraser. There we go. So, lambda equals, what did we get? 11 meters. So that's the wavelength for the diathermy machine in physiotherapy. Another straightforward problem, we just plug it into the formula and solve for the wavelength. Problem 61. We are asked to find the wavelength range for AM radio, which broadcasts 540 kilohertz to 1600 kilohertz. And then we're asked to find the wavelength range for FM radio, which is broadcasting 88 megahertz to 108 megahertz. So let's do part A first for AM radio. AM radio, 540 to 1600 megahertz, right? We're asked to find the wavelength range, so let's just take the first one. Lambda, we'll call it lambda AM1 is going to be C times 1 over the frequency, which is 540 times 10 to the 3 hertz, right? And that's going to equal 187.5 meters. Remember that this is 3 times 10 to the 8 meters per second. And this is actually hertz, which is 1 over seconds. Okay, and then next one, AM2, C over 1.6 times 10 to the 6 hertz, because we had 1600. Oh, sorry, I wrote this down wrong. In the problem, we're given kilohertz. So I said megahertz, it's kilohertz. That's how we get this value. So, C over 1.6 times 10 to the 6 hertz gives us a value of 555.55 meters. So that's the range. So for AM, we're broadcasting 187.5 to 555.55 meters. Those are the wavelengths range. Right? Now, for FM, FM1 equals C over, what was it? 88 megahertz. So 88 times 10 to the 6 hertz. This gives us a value of 2.77 meters. Again, over 108 times 10 to the 6 hertz gives us a value of 3.1 meters. 3.41 meters, excuse me. So, again, just before I write this down and finalize these problems, C is the speed of light, 3 times 10 to the 8 meters per second, right? C is equal to 3 times 10 to the 8 meters per second. So that's what I'm plugging in. The unit of hertz is equal to 1 over seconds. Just reiterating in case anyone is confused or has forgotten since the last problem. So FM, our range of lambda, is going to be 2.77 to 3.41 meters. Great.